All right, hello again, everybody. So now I'm going to handle the next two parts of this review, which are some, let's see, I'll hop back over to this page. These are finding a tangent line of an implicitly defined function, so I'm going to have to use implicit differentiation for that. And then finding some critical points. And some min-maxes. I think I'm going to just do all of these in one session and then come back and do optimization related rates. Great. All right. So let's get into it. Okay. So very briefly reviewing what an implicitly defined function is. An explicitly defined function would be something that I have in terms of y or in terms of x. So a y equals usually, or an x equals, or just a variable that doesn't also appear on the other side of the equation. An implicitly defined function is just something that's not that. And so these functions, for instance, this one, are not going to be easily solvable in terms of x or in terms of y. And I really don't want to think about trying to do that, so I'm not gonna. Okay, so here we go. So in order to do this, we're going to do some implicit differentiation. So this means taking the derivative of both sides with an understanding that we're taking y to depend on x here. So we consider y as being a function of x. And then we're going to say y, okay, no, that's not what I wanted. So let's just go through this. So 4x cubed is the derivative of 4x. So let me actually say this. Differentiating implicitly, we get the 4x cubed minus 3y cubed derivative of that. So I'm going to take the derivative of 3y squared, 3y cubed, minus 3y cubed, I guess, but that's going to give me 9y squared. But because y depends on x, I have to use chain rule, which amounts to just saying I multiply by the derivative of y. So that's going to be y squared times y prime. That's all I get. Okay, moving right along. I have xy now, so that's going to be a product rule situation. So if I differentiate the x and leave the y alone, I believe I just get a y. And then if I differentiate the y and leave the x alone, I'm going to get an xy prime. Okay, so that deals with the xy. The 25 gets differentiated away, and I have a 0 on the other side because I just took the derivative of 0, and of course that's still 0. Okay? So now my next step is going to be I need to solve this for the slope. So that in this case is y prime. If I were looking for a generic formula for the slope, then I would have to actually solve for it explicitly. But in this case, I just need the slope at the given point. So here's what I'm going to do. I'm going to solve for it algebraically and then plug in. Or I can plug in and then solve for y prime numerically, basically, right? So solving algebraically, I'm going to put all my y primes on one side so I can factor y prime out. I'm going to choose to bring them over to the right side. So I'm subtracting everything with a y prime in it over to this side. And let me go one step further and factor that out. So I've got 9y squared minus x y prime. And so that gives me pretty immediately y prime equals, gotta display my style, fraction 4x cubed plus y over 9y squared minus x. So if I were being asked to use implicit differentiation to find y prime generically, this would be where I would stop. But I need it at -1, 2. So I'm going to punch in -1 for x and 2 for y. So y prime is going to be 4 times -1 cubed plus 2 over 9 times -1 squared, or sorry, no, this is 9y squared, so it's 9 times 2 squared minus -1, right? And so let me get a better look at this. That looks like it's going to be a -4 plus 2, so a -2 on top. And then the bottom, I think, is going to be 37, which is a bad number, but okay. Negative fraction 2 over 37. Okay. So that's one way I can do it. The other way is to just plug in the first place, and that's going to make my life a little bit easier because I don't have to wrangle with this. So I'll say, or solving numerically, we get, so this means I'm going to plug in first. So I have 4 times -1 cubed minus 9 times 2 squared y prime plus the 2 from the y. Yeah, that's what I want to do. Plus -1 times y prime. Equals 0. Okay. And then you could solve that out. You're going to get the same thing for y. I just wanted to show you a couple of different but equivalent ways. You're doing the same thing in 2 different orders, so it's the same. You're going to get the same result. So now either way, I have my slope and I have my point. So now I have my point, so can use the formula from before when I did all these tangent line problems. I guess that's going to be in a different video. So this will be y, okay, so tangent line equals y equals, slope comes first. Let me move that negative outside the 2, and let me display style, times, let me see, x minus a -1 plus 2. And this is a case where it would be really kind of silly to write the whole thing out because you'd have to do fraction computations and stuff, and I don't really think that's helpful. So I'm just going to make that an x plus 1 into parentheses, which is what it really is, plus 2, and just leave that there. So that's 1, and the next one will not take as long. Just as soon as I can pull up what it is. Ew, okay, well that's all right. This is gonna be cosine of x squared minus y times pi plus x cubed minus y squared plus 3xy equals 0. And that's going to be at the point 1, 3. Okay, this one looks a lot worse, but really the only thing that's going to be worse about it is the differentiation part. So let me just do that first. Differentiating. You know, doing something like this is very affirming for me because I get to look at my little face over there on the other screen, and I get to hear my lovely voice, and it's very nice. Okay, so first things first, let's take the derivative of the cosine thing here. So that's going to be negative sine of whatever's in there. And then I have to, let's see here. That looks like it's going to be, I have to bring the derivative of the inside and multiply by that, right? So I think I'm going to say dot and then 2x minus y prime times pi. So that's what I would get if I differentiated the thing on the inside. Okay, and now the rest of this goes pretty straightforward. So 3x squared minus 2y y prime. Yuck. And then plus 3, here comes a product rule. Differentiate the x, leave the y alone, that's the y. Differentiate the y, leave the x alone, that's x y prime. And that's all equal to 0. And this is so bad that it takes up more than one line, but that's okay. So this is an example where trying to algebraically simplify this is just going to make it really bad for you. Hold on a second, I'm getting a call. Hello? Hello? I'm sorry, you're not coming through so well. I think you may have the wrong number. Hello? Oh, that was interesting. Where was I? If I had a video editor, I could edit that out, but I don't. So let's see here. So if I try to solve algebraically for y prime here, I could, but I'm going to get something that's really bad, and I would rather not do that. So let's just plug in my 1, 3 and see what I get, and then solve algebraically. So I'm plugging in first here, and I'm going to get sine of 1 squared minus 3 times pi times 2 minus y prime times pi plus 3 times 1 squared minus 2 times 3 times y prime plus 3 times y is 3 plus y prime. equals 0. Hopefully this is a little bit more amenable to that, just barely fits. Okay, so this looks bad. It's about to get much simpler. Here's the first thing I want you to notice. This whole thing contains a sign of an integer multiple, it doesn't matter what that is, an integer multiple of pi. That automatically makes this whole term 0. So I'm just going to drop that. And then what do I get? I get 3 minus 6y prime plus, just going to distribute that out, 9 plus 3y prime equals 0. If I group everything up, it looks like I'm going to get 12 equals a 3y prime, or y prime is just 4. So that's nice. That means my job is going to be a little bit easier because this is not such a horrible thing that I have to wrangle with. So let's see. Oh, I just want to, whenever I pull a trick like I just did, I want to be clear how you could have just very well easily put sine of negative 2 pi into your calculator and got 0, and then you would have known you could get rid of this whole term. Or you could have algebraically simplified it, and you would have gotten the same thing. So the trick that I pulled is not necessary to solve this, it just makes it a little bit faster. Okay, so my tangent line is y equals, slope comes first, 4 times x minus my x value is 1 plus 3. There you go. All right, that does it, but that about does it for implicit. So you have two ways of doing that now. Okay, now find the critical points of the following functions. So f of x, before I jump into an example, I should probably say a little about what a critical point is, just for the purpose of review. So critical points of a function on an interval. So critical points always have to do with a function. They belong to a function. And typically you're going to be asked to find the critical points of some function on a given closed interval. You might have to do critical points on the entire real line. I certainly see one example for which that is true. But most of the time, you're just going to have an interval. A closed interval is what I mean when I say that. So what are these? The 5-second definition is the places where maxima or minima can be. There are 3 kinds of critical points. Derivative of the function is 0, so wherever the derivative is 0, I'm going to automatically have a critical point. The derivative of the function is not defined or doesn't exist, or the endpoints of the interval if they are finite. Well, let me say if they exist as finite numbers. That's a little bit more mathematically inclined way of saying that. Okay, so just right now, my mission is for each one of these to figure out all of these guys for a given function on a given interval. And once I've done that, I am good. I could list them in left to right order or any order I like or whatever. But ultimately, this is all I need to do. So let's start with something simple. F of x equals sine of pi x on the closed interval 0 to 5. And now, so the first thing I have to do here, the endpoints I know already, those are given to me, in fact. And so the first thing I should do here is take the derivative, because the other two require me to do that first. So first, let's say f prime of x, that's going to be pi cosine pi x. Uh-oh. And then I've got f prime of x equals 0 implies cosine of pi x equals 0, which, let's see here. So I have to think about what values make cosine 0. So I claim that cosine is 0 when x is pi over 2 plus an integer multiple of pi. So if you think about it, if you think about your unit circle, hopefully you can see that. So this is like, I'll start with negative numbers. So negative 3 pi over 2, negative 1 pi over 2, positive pi over 2, 3 pi over 2, and so on. That sort of thing. So let me see here. Just off the top of my head, pi is about 3. I have a math degree, so I can say that. Pi over 2 is 1.57, so it's about 1.5. So 3 pi over 2 is going to be about 4.5. So I think I can say without using my calculator that 3 pi over 2 and pi over 2 will lie on this interval, and that nobody else will. So we'll say on this interval, this gives x equals pi over 2 as a critical point, and x equals 3 pi over 2 as a critical point. So then we have to contend with, does this thing ever not exist? If that never happens, because cosine is defined everywhere and it's, yeah, it doesn't have a problem anywhere. So what we're looking for when we do this is something like dividing by 0, usually. But in this case, that never happens. And then we need the endpoints, which are x equals 0 and x equals 5. Oh, I missed a trick up here. So, shoot, yeah, I did kind of mess up. So, let me correct myself here. I just realized I got a little carried away. So let's say cosine of pi x is 0 when the thing I'm taking the cosine of, so in this case, that's pi x. So I need, if I cancel the pi, x equals n plus 1/2. And so there's a few of these I can have. This is going to give me x equals 1/2, 3/2, 5/2, 7/2, and 9/2. So 1/2, 1.5, 2.5, 3.5, 4.5. Oh, that's a little tricky to look at. All right, so critical points. If I was being really thorough, I might plug these into the function. But I'll just say x is 0, 1/2, 3/2, 5/2, 7/2, 9/2, and 5. Whew, okay. I think how many more do I have? I have 4 more, and then some other stuff. So f of x equals, sorry, we're doing the next one now. G of t equals t cubed minus t on 0 to 1. So, same story. First thing we do is take the derivative, that's 3t squared minus 1. I'm just going to go ahead and get this one out of the way and observe that derivative is never undefined. So I can just take that and throw it away. Set g prime of t equal to 0, which gives me 3t squared equals 1. So t squared is 1/3. So t could be plus or minus 1 over the square root of 3. On this interval, I type this interval. On this interval, we just take t, the positive value, \1. That's not going to be okay. All right. And then I have my endpoints, which are x equals 0, x equals 1. Or sorry, t, not x. I don't know what I was thinking there. Force of habit is what it was. Okay, C. This is going to be h of z. That's a typo. It's going to be h of x equals negative x squared plus 6x plus 8 on negative 7 to 7. First order of business is find h prime. And can I just say that's 2x, that's minus 2x plus 6. I'm going to observe again that this is never undefined. And then I set it equal to 0. And that gives me 6 equals 2x. So x equals 3. So x equals 3 is my only critical point besides the endpoints. So critical points are, I'm just going to start throwing the endpoints in without saying what they are. X equals negative 7, 3, and 7. Okay, we're moving right along. G of x equals, this is the next one now, g of x equals x squared minus 5 times e to the x on, oh boy, let's see how much this program can handle. On the real line, which is an open interval, negative infinity to infinity. Okay, good, it does render that. So, all right. Yuck. First order of business is take this thing's derivative. So that's going to be product rule. G prime of x equals, first I take the derivative of the x squared minus 5, leave the e to the x alone, plus x squared minus 5 e to the x. Once again, I will observe this is never undefined. So I need to set this equal to 0 now. And here's what I'm going to say. This looks like it's bad to set equal to 0, but it really isn't that bad. Those numbers are going to be something, though. Might be easier to change the numbers, but I won't. Okay, yuck. Yuck. At least those are nice quadratic formulas. Okay. So I looked ahead and did the solution in my head. So this is going to be, I'm going to factor this e to the x out. And I'm going to say 2x plus x squared minus 5 e to the x equals 0. 2x plus x squared minus 5 equals 0, or e to the x is 0, but e to the x is always positive, so it can't be 0. So really, I just have to find the zeros of that quadratic equation. And to do this, I could complete the square, but I'm going to just use quadratic formula, hit it with a hammer, because I'd like to get this over with faster. So let's see, negative b plus or minus square root of b squared minus 4ac all over 2a. Oh, God. And I'll save you the trouble here. That's going to be, let's see here, -1 plus or minus square root of 6. Okay, square root of 6 is about 2.5. So it's a shade less, it's about 2.45, but it's about 2.5. Really doesn't matter here. I don't have to restrict myself to the right interval because the right interval is everything. Because the interval is the whole real line, that means that the endpoints are not finite numbers, right? They're infinity and negative infinity. Well, I can't plug infinity into a function, so I'm not going to say that's a critical point. That would be wrong. So that means that these ones I found here are the only critical points. -1 plus or minus square root of 6. And I'm going to put in a little cautionary note on the endpoint. So why am I doing that? So a critical point, remember, is where a max or a min can occur. And in the sense we think of a function in calculus, where a function is something that you plug something into, I have to pick a finite number to plug into. I can't use infinity. So we can't say it has a maximum at infinity, so infinity cannot be a critical number. That's really what's going on here. All right, we have one more of these. On -2 to +9. I do not know if I like this. That's okay, we'll just take the derivative here. This one also does not look like it will have problems here. I've got a product rule. I'm going to leave the e to the y alone. Or sorry, I want to differentiate e to the y first, leave sine of y alone, plus I'm going to leave the e to the y alone, differentiate the sine of y, and that's going to be a cosine. And so for the same reason as before, I am not going to have any zeros out of this e to the y, so I can factor it out. I will divide it out with impunity. Let's see, e to the y, that's then sine y plus cosine y. Great. So derivative never undefined. Derivate, that's either not a word or a very good word in Scrabble. I'll have to look it up. Be a good bingo too, that V is juicy. All right. So equals 0. For the same reason as above, this is going to give me e to the y is 0, or sine y plus cosine y is 0. So remember, the first one of those is impossible with real numbers. And let's see. So I have to solve here sine y equals negative cosine y, or tangent y equals negative 1. Uh-oh. How'd that get there? And so how I would prefer to think about this usually, when I think of tangent, I think of slope. Partially because the slope of the tangent line is something you hear all the time, and because if you think of your unit circle, and I drop a straight line on that unit circle that goes through the origin, then the tangent line, the tangent of whatever angle that line makes with the positive x-axis is going to be a, where was I? Sorry, I had a moment there. So I drop a line, it goes through the origin. That line makes an angle with the positive x-axis. It is a fact that the tangent of that angle gives me the slope. So if I want to know what points on the unit circle, what angles, have a tangent of -1, I can just superimpose in my brain a line with slope -1 and think about where those go, where that hits the unit circle. Specifically, it's going to be y equals so 0 to 2 pi here. Let's see. So one of those is going to be 3 pi over 4 and 7 pi over 4. But tangent has a period of pi, right? So I need to get all the points for which tangent is -1 on this interval. So I'm going to keep adding pi's until I go over 9. That sounds like a good evening, keep adding pi's. 11 pi over 4. And I believe if I added 15 pi over 4, that would be a shade less than 4 pi, which is 12. So that's going to be more than 9. And then I need to start going backwards. So if I subtract a pi from 3 pi over 4, I'm going to get a negative pi over 4. And if I go another pi to the right, or to the left, sorry, I'm going to go past -2, so I think I can leave that alone. And we already agreed that this derivative was never undefined, so the critical numbers, critical points, are these together with y equals -2. My computer was lagging just real bad. And y equals 9. Okay, that wraps up critical points. Except it really doesn't, because the next thing I'm going to do is maxes and mins. I have just done the first page of this. I have 3 more. I've been at this for 2 hours. Great, okay. So let's see. Let's just get this done, huh? So find the minimum or maximum of the following functions. Okay, I'm gonna have to stop the recording here and pick up in a minute because my computer was lagging too hard to type. So I'm gonna delete this and say stop. So next part will be, let me see, the next part will be minima maxima. So